Okay, class. So today we'll look at dimensional analysis, and then we'll start with why we perform dimensional analysis, and then followed up by the Buckingham Pi Theorem, which used to conduct a dimensional analysis, and then we'll end up with an example problem. Okay, so there are two reasons why we need dimensional analysis. The first one is, well, we need to do experiment, but when we conduct experiment, most of the cases we cannot use the original size. So how to use the data obtained from experiment with different size to inform the design of a prototype. And dimensional analysis provides a systematic method to bridge the gap. Second reason we conduct dimensional analysis is because it provides a better way to represent experimental data. Well, I want to use an example to explain why dimensional analysis provides a better way for experimental data. Okay, so for example, if you are sent to an alien planet where, well, we don't know it's we want to perform experiment is a falling experiment, and given initial velocity and given height, and also on the planet we know there is a gravity, and the question we want to answer is the time required for the falling experiment. Well, if we know the Newton's second law, and then we can do theoretical calculation, well, we're assuming that we don't know the underlying physics, but we want to perform experiment to understand or lead to the understanding of underlying principles. Okay, so, and then we do some preliminary results. We will figure out that t will be a function of a velocity, initial velocity, height, and the gravity of that planet. Well, as a result, we can continue to do some experiment. And for example, we can fix height and g, and we can do a series experiment, and we'll see that t will change with the initial velocity. Similarly, we can conduct another experiment, well, t as a function of h by fixing velocity and g, and if we're able to go to a different planet, and we can also conduct another experiment, t will be a function of g. So based on the series experiment, but we still cannot answer a question that given VHG to find time, because when we do the three set of experiment, we fix two values at change one. So it's very hard to map any to any given VHG. Okay, so dimensional analysis for this problem can help us find magic parameters, or in dimensional analysis, we also call them pi terms. In this case, we can use two variables or two parameters. The first parameter is on the right side of the equation, left side of the equation, called pi 1 is t over h and divided by v. And the right side, we have another magic parameter. It is gh over v squared for this problem. If we plot pi, the first parameter as a function of the second parameter, well, you'll see that no matter how you change GHV, all the data points will collapse on the same curve. As a result, we solve the problem that given any GHV, we are able to find t based on the experiment we have performed. And also, because all the curves collapse on the one curve, one line here, so that means we don't need to conduct so many experiments that reduced the experiment. So that's why we call that dimensional analysis provide a better way to represent experimental data, and also provide better way to design an experiment. And then we come to the next slide, where the method to conduct dimensional analysis. Here we call the Buckingham Pi Theorem. It can reduce the number of parameters for the equation. For this problem, we know that t will be a function of VHG. After dimensional analysis, so we reduced parameters involved into 2, and we call those dimensionless parameters is called pi terms. And in general, if you look at the equation below, so the equation will become a more general form. The pi y will be a function of pi 2 to pi r, and r in general will less than n, that for original equation. Now, before show how to conduct the Buckingham Pi theorem, we first review the basic dimensions. So in basic dimension, there are two sets of kind of basic dimensions: MLT, and then temperature charge, or that we can also use the other set is FTL, temperature and Q charge. So use this 5 dimensions, we call them basic dimensions. We can express any other physical quantities in terms of basic dimensions. So a quick example is, for example, if we want express dimension of a velocity, we know velocity is is length divided by time. So we can express the dimension of velocity as L over T. So you can extend this to any other physical quantities as long as we have the basic dimensions. And in fluid mechanics, most of the time, we only need 3 of them, either MLT or FLT. Now we come to a problem, and we use this problem as an example to show how to perform Buckingham Pi theorem to perform dimensional analysis. So the problem we have here is we have plate with width W and height H, and there's a fluid will come across this plate, and with velocity V, density rho, and viscosity mu. As a result, there will generate a drag force, and the drag force will be a function of all the parameters involved. Okay, to perform Buckingham Pi theorem, the step 1 is to list all variables involved. I will put the dependent variable F, in this case the drag force, on the left side, and the rest WH mu rho V, so independent variables, on the right side. And F here, so the lowercase f here represents the function or the physics behind. And for dimensional analysis, we don't need to know exactly what kind of physics is involved, and because the purpose is to reduce the equation without knowing what kind of equation it is. Step 2 is express all variables involved in terms of basic dimensions. Either use FLT or MLT. And for this problem, we can let's choose FLT. So either way, if you use FLT, then force will be F, WH, so basically their dimensions will be L, viscosity is F times T over L squared, and then density is F times T squared over L cubed, and then velocity is L over T. Now we go to step 3. We will count the number of pi terms. So eventually, that how many pi terms we'll have. Well, the number of pi terms equals the total variables involved. For this problem, the total variable involved is 6, include both left side and right side, and then minus the reference dimensions. So now here's a question: what is the reference dimension? Well, reference dimension in most cases equals basic dimensions involved, and there's exceptions, and we'll talk about exceptions later. So we will assume here that reference dimension is basic dimension. In this case, we have F, we have L, and T. There are 3 basic dimensions involved, so that's 3. So total variable minus reference dimension, 6 minus 3 is 3. That means at the end, we should have 3 pi terms. The next step is a key step for the problem. It's called select repeating variables from the right side of the equation. So there's a few principles to select repeating variables. First, it must from the right side of the equation, from independent variable, and then the repeating variable, number of repeating variable equals the number of reference dimensions. So in this problem, we have 3 reference dimensions. That means we'll choose 3 from the right side of the equation. And it must include all basic dimension involved. In this case, it's FLT, so we need to choose 3 that can include F, L, and T. And then repeating variable, followed by the other 2 principles. First is repeating variables are independent with each other. So now there is a keyword independent with each other. So example is, well, if we choose W and H as the repeating variable and plus the other ones, because we need to choose 3, but let's see here, the W and H, they are not independent. The reason is because they both share LL, the length, basic dimensions, so they are not independent with each other. Another example is if you choose, see that if you choose a dimension, choose a variable whose dimension is t, and then another one is L, and another is L over T, and these 3 are not independent because L over T can be expressed by T, by L over T can be expressed by the other 2. So in general, you cannot choose the variable that can be written in a form that, see that variable 1, variable 2, in general, variable, let's say n, if each of them raised by exponent alpha, beta, gamma, z, and k, you cannot make them equal to 1 by finding appropriate alpha, beta, k exponent. So for this particular problem, that as long as we don't choose W and H at the same time, so it's safe. Okay, and the next one is the set of repeating variables are not unique. Well, it's based on the previous principles. You will see that there's many ways we can choose. So for example, we could choose, here we could choose H, mu, and rho. It works because it's meet the previous 3 principles. Or we can choose W, mu, and V. It also works. And you can choose there's many other combinations. And for example, we can choose H, mu, H rho V. It still works. And in general, that there's many ways to choose repeating variables. Okay, so now we go to the next step. The step 5 is the calculation computation step. So we will use repeating variables to now dimensionalize the rest variables. So let's say that we choose repeating variable H mu V, which, as we have discussed, this is not unique. You can choose other repeating variables, but here let's choose H mu V, and then our job is to now dimensionalize FW rho. So we'll do it one by one. We'll work on F with the repeating variable, and then work on W, and then work on rho. And we call it repeating variable because we'll keep using H mu V, the variables we choose, to now dimensionalize the rest. I'll use F as an example, and then can be extended to W and rho. So for F, first step is we F, and then we times the repeating variable we choose. And for the repeating variables, each of them will raise to an exponent term, alpha, beta, gamma. And the purpose is that we want to now dimensionalize F using H mu V. So we'll make this equation equals 1. And this dimensional analysis will replace all the variables by their dimensions. So in this problem, we replace F by F, H by L, and mu is the Ft over L squared, and then V is L over T. And the next step is we will group F term together, L term together, T term together. And for f term, we have f to the power of 1 plus beta, and L is alpha minus 2 beta plus gamma t to the power of beta minus gamma equals 1. So the only way to make this equation equals 1 is all these exponent terms become 0. And that leads to an equation that all their exponents equal 0. And we get 3 equations, 3 variables. We have 3 alpha, beta, gamma unknowns involved. By solving these three equations, we get alpha, beta, gamma. So once we have alpha, beta, gamma, we put alpha, beta, gamma back to the most top equation here. And for the right side, that will be our pi terms. So the first pi term obtained will be f divided by h times mu times v. Similarly, we can extend to w, and we can do exactly the same thing, but replace f by w, and we'll conduct the exactly same thing. And because we replaced f by w, then we'll get different alpha, beta, gamma. Again, the result will get different pi terms, which is a pi 2, as shown here. It's w over h. If some of you have a keen observation, you will notice that w and h share the same dimension. So instead of go through this process, if you have keen observation, you can use h itself to not dimensionalize w. That's w divided by h. It will become dimensionless. So we can get pi 2 terms directly if you know they share the same dimension. Well, and then you can work on rho and then replace the first term, the first variable by rho, and then you go through the same process, you will get pi 3. And then you can go to the last step, and then you can write into a new function. So originally, we have a function that f is a function of wh mu rho v. What kind of function it is, we don't know, and you don't have to know it. So the core problem is to reduce the equation without knowing it, and we get a new set of equation. And to the right side, we have pi 1. This is a pi 1 term, is a function of a pi 2 and pi 3. So pi 2 and pi 3. As once we have this pi equation, and we can use it to reach 2 goals. The first one is to bridge the gap from model to prototype. And second one is a better represent experimental data. Okay, so we'll stop here, and you will have a quiz problem which has been uploaded to Brightspace.